here, and today let's go ahead and continue with our exercises in quantum field theory for the gifted amateur. So today we'll be doing problem 36.1, an illustration of the reason for anti-commutation and spin. Part A, we're going to do all the way to part C, everything. So part A, show that the Dirac equation can be recast into the form I this thing equals to HD, where HD is the Dirac Hamiltonian in terms of alpha and beta, where these are in terms of the gamma matrices. So we're supposed to find alpha and beta in terms of the gamma matrices. So let's go ahead and go to the Dirac equation, find what's this original form. So I believe it is I believe it's here. So yes, so we have, okay, go a bit higher. Okay, yeah, so we start off from here. So we have this over here. We have this equation. So these gamma matrices are defined in terms of their anti-commutation relations. So let's go over to okay. Okay, so we have gamma p naught minus gamma dot p, where these are like this, and this is a vector, and this is the operator. Then minus m psi of x equals to 0. Okay, so first of all, let's keep this like this, and then we know p naught is equals to we know p naught is equals to I derivative with respect to time equals to gamma dot p plus m psi of x, and this is okay, so now we are almost there actually. So we just see that we need to get rid of the gamma naught. So how do we so-called divide it out? Well, it turns out we don't divide it out, we multiply it. So from here, in order to get it into this equation, we just need to multiply both sides by gamma naught. So when you multiply, then gamma naught squared I dt over d over dt of psi equals to gamma naught gamma dot p plus gamma naught m psi, and because this is equals to the identity, so it's equals to just 1, it's the identity matrix. And then if we write it in terms of alpha dot p plus beta m, then we immediately see that alpha equals to gamma naught gamma, so this is a vector, it's a 3-component vector sort of, and beta is equals to gamma naught. So these are vector, and this is a vector quantity. I mean alpha 1 equals to gamma naught gamma 1, alpha 2 equals to gamma naught gamma 2, and alpha 3, that's what I mean by vector, and beta is equals to gamma naught. So yeah, so we have done the first part A. Okay, so evaluate HD squared and show that the Klein-Gordon dispersion, show that for Klein-Gordon dispersion we must have these two properties. So let's go ahead. So we know H equals to alpha dot p plus beta m, where these are the defining relations for alpha and beta. So then H squared is equals to so we have alpha 1 p1 plus alpha 2 p2 plus alpha 3 p3 squared plus the cross terms, but remember that it's it's not commutative, so we need to be careful. So we have alpha beta plus beta alpha p, then this is a dot p m plus beta squared m squared. So this is h squared. Now we realize that these terms, they are simply alpha 1 alpha, so there are actually alpha 1 squared p1 squared plus alpha 2 p2 squared plus alpha 3 alpha 2 squared alpha 3 squared p3 squared plus alpha 1 alpha 2 plus alpha 2 alpha 1 bracket p1 p2 plus alpha 1 alpha 3 plus alpha 3 alpha 1 p1 p3 plus alpha 2 alpha 3 plus alpha 3 alpha 2 p 2 p3, and then this term is simply alpha 1 beta plus beta alpha 1 and so on for 2 and 3. So the first term is the one that multiplies by p1, second one is by p2. Okay, maybe this is a bad notation. I'll remove the bracket here. Times m plus beta squared m squared. Now, what does the question want us to do? It tells us that it wants to have the Klein-Gordon dispersion relation. So what this means is that it wants h squared of psi to equals to, we know that h, eigenvalues of h is energy, so we know this, and we know that a Klein-Gordon dispersion relation is E squared equals to P squared plus M squared. So essentially, we know, what do we notice here? We notice that this P squared over here that we want is these P squareds, and then this M squared we want is this M squared, and then the rest of the terms, all of these other terms, we want them to disappear. So what do we need? We need the matrices alpha 1, alpha 2, alpha 3 and beta to satisfy certain properties, namely alpha 1 squared equals to alpha 2 squared equals to alpha 3 squared equals to the identity. Then we want all the anti-commutators to be equal to zero matrix for I not equal to j. Then we want alpha I beta plus beta alpha I to also equal to 0, and we want beta squared to be equals to the identity matrix. So we realize that this is just the anti-commutator, and this is just the anti-commutator as well. So yeah, so then we realize that so all the alpha I objects and beta objects anti-commute, you see with this second and third line, and then we have all the alpha I squared and all the beta squared equals to the identity. So we have in fact proven these two relations. Okay, so this provides some justification for the anti-commutation relations we imposed on the gammas, indeed. So now we prove the commutation relations. This one requires a bit more manipulation, but let's go ahead and do it. It's not too hard either. So what are we given? So we have the Hamiltonian, which is given by this Hamiltonian. So we have h equals to alpha dot p plus beta m, where remember that alpha and beta are matrices, so they do not commute. Okay, and then we have angular momentum L equals to x cross p. So in summation in indices language, where this is the Levi-Civita symbol, this is J and this is K, PK. Yes, that is true. Okay, so then if L is an operator, then we make these operators as well. So yeah, so this is just the Levi-Civita symbols. Okay, so So now we compute the Hamiltonian, the commutator of the Hamiltonian with the angular momentum. So what do we get? We just plug it in first. So what can we expect from this? Okay, so a few things to note. There are a few things that can commute and they do not, and a few things that do not commute. So we know for one, matrices, what can we look out for? We look out for matrices that don't commute. So these are no commute. Not so nice. And second thing is operators. Okay, so what do we see over here? We see that alpha is a matrix, P is an operator, beta is a matrix, M is a scalar only. So and then on the right hand side we have no matrices, we only have operators. Okay, so what this means is that the matrix is essentially in a sense blind to this commutator. So we can pull them out as if they are constants, because the matrices we don't have in the two blanks, right, in the two arguments, in the two positions, I mean in these two things, there's a matrix here, but here we have operator only. So here we have operator, on the left we have operator and matrix, and on the right we only have operator. So the matrix essentially acts as constants. So what this means is that, okay, first of all, the M and beta, they don't commute. So we can the commutator is 0. So it's just this. And then on the other hand we have this, which is just 0. This is just 0 because this guy is a matrix and this guy is a number, and these guys are operators. They do not talk to one another. Yeah, they can commute with one another. So we don't have this thing to focus on. So writing in index notation, if the Levi-Citadel symbol, it can be pulled out. So we simply get ijk, then we let this we do the dot product via a summation. So we let it be m, let's say, and then we have pm. Okay, let's just xj pk. Okay, then we have this ijk. Then now we can apply the rule for commutator, namely that a with bc equals to a with b c plus b with a and c. So what this gives us is a with b, and then we have c, yeah, and then we have c, which is pk, plus we have b, and then p, m and pk, and so we have ijk, and then on the right this thing is equals to 0 because the momentum, different components of the momentum commute. Then this thing is minus ih bar, this with m and j, and we have pk. So a summation over the indices, let's contract them. So m gets replaced with j. Wait, sorry, I forgot this alpha m over here. So there's alpha m here, alpha m. So alpha m, so it's alpha j, it's an ijk, pk, and this is equals to, oh, okay, let h bar, in this case they use units where h bar is equals to 1, doesn't really matter, it's just a constant. So we have I is ln ijk, solve the indices with and pick up a minus sign. Okay, we solve the indices and pick up a minus sign, so it's just p j alpha k, and this is simply I, the cross product of p with alpha in the ith component. So yes, we have shown this. Okay, so do note that this I is the index, it's not the complex number. Okay, so now for part 2. Okay, so for part 2, let's go on to a new page. Okay, so what do we have? We have now we have the definition that, so we have, once again we have H. I just write the definition for easy reference, and then we have the S operator, the spin operator. So the spin operator is a matrix. So do note that Hamiltonian is a matrix and operator, and this spin operator is simply half of this summation symbol, this sigma symbol, which is gamma cross gamma. So what does that look like? It's I over 4. Once again using the Levi-Civita symbol. Then you have J, K. So this is just a matrix, it's not an operator. So now the commutator only sees the matrices because they are the only common objects. So H with Si equals to I over 4 ijk. Now once again beta m. Now you realize that beta m is okay, so now beta m is a matrix as well. So both these objects, they have to be in a commutator. You have to care about them. So this is, now we have alpha m p m. This is j k plus beta. What is beta? It's just gamma naught m, and then this is gamma j, gamma k, and there's a factor of m there. Okay, so let's go ahead. I over 4, we can write these down all day. So the first thing to evaluate here is this object. Now what is now we can actually pull out pm. Okay, so I'll choose to write them separately. So alpha m pm alpha j alpha k is simply equals to pm. We have pulled out pm because pm is an operator, it's not a matrix, so it's blind to whatever matrix stuff there is inside. Then there's pm, I mean this thing and this thing, and then there's so what's this thing? Now let's go through some stuff. So this, by definition, well, there's no shortcut, we just have to multiply it out. Okay, then this one, so the goal here is to express it as gamma naught in terms of some stuff. Okay, and we're sure that the some stuff is going to be actually is going to be quite nice. Okay, so in order to do so, we need to bring this gamma naught, this matrix, over. We need to make 2 jumps. So how do we do that? We get the first term, just copy over, minus. So let's do the first swap between these two. Okay, so how do we do the swap? We notice that gamma k gamma naught plus gamma naught gamma k is equals to 0 because gamma I gamma, or rather gamma mu gamma nu, the anti-commutator, is equals to 2 g mu nu, where this is the, where this is this thing, is the Lorentz metric. So these things anti-commute, so when you bring them over, it's simply pick up a minus sign, so it's just this. Now same thing, we can do it for these two, okay, and because this is because k is not equals to 0, k is equals to 1, 2 or 3, that on the right hand side, that's the reason for this being a 0, because you're doing a 0 with one of these guys and all of them are 0. So this is just this minus gamma naught gamma j gamma k gamma m. Okay, this is where it gets a bit more interesting. So we can factor out gamma naught. Now we need to bring them to be similar. So in order to do so, we need to swap these two first. You see, we want to bring gamma m here, right? So this is going to be gamma m gamma j gamma k minus gamma j. And what is this? This is just 2 minus canonical delta of k and m minus gamma m gamma k. Yeah, so this is just gamma naught gamma m gamma j gamma k okay. So yeah, so then this guy, you can ignore it for now. We just want to make these guys cancel, so let's do this swap next. So this is gamma naught gamma m gamma j gamma k plus this guy would be minus gamma jm okay, and this will be gamma m gamma j gamma k. Okay, so this guy, realize that is actually minus gamma m gamma j gamma k. These two cancel nicely, and then what are we left with? We're left with minus 2 gamma j m gamma k, I mean delta, plus 2 delta k m delta j. Okay, then now here we have minus, so now we have 2. Okay, so it's time to substitute it back in, but let's write it nicely first. So we have 2 gamma naught sigma km gamma j minus sigma jm gamma k. Okay, so let's substitute it back into here. So we had what was the equation that we're looking for? We're looking for this. Okay, so substituting it back in, we have gamma pm so this guy will be pm, so will be I over 4 canonical delta pm, then this will be 2, so 2 makes this 2. Then we have gamma naught okay, then we zoom in here. So we have I over 2 Levis Civita pm. Okay, then this guy replaces k, so we have gamma naught, but this guy will replace m with k, this guy will be gamma j, then this guy, and then on the other guy we have I over 2, this guy with this guy, so they replaces m with j, then there's this. Okay, so what do we see? We see, okay, then let's do some swapping of indices. So this is I over 2. First of all, let's write it as k, then this is j minus I over 2 Levi-Civita p of j alpha of k. Then let's see, with almost the one we want, so let's do a swap of the indices here. P of j, so do a minus sign, then this is a alpha k minus I over 2, the exact same thing, and this is equals to minus I, this, and this is equals to p cross alpha in the ith component, so where these are like vectors. So we have in fact almost there, or have almost shown it. What is left to show is that the beta part, which is this part, it vanishes. I think it's pretty obvious because we have already showed most of it. So we need to show that the commutator of gamma naught with these guys, they vanish. So let's do it. So gamma naught, gamma j, gamma k, commutator of these is equals to so commutator of these is equals to gamma naught, gamma j, gamma k minus gamma j minus gamma k, gamma naught. Then there's some anti-commuting to do. So this guy swaps over with this guy, picks up a minus sign, and it swaps over again. So I'll just write it out clearly. This guy should, it's just a indeed. Okay, so then this guy is gamma k plus, this guy is a plus plus, then this guy swaps with this guy, so it's a minus gamma, not gamma j, gamma k, and this is clearly just 0. So what we have shown in fact is that the commutator of the Hamiltonian with the spin consists of commutator of a matrix and operator with a matrix. Well, the operator just factors out as a constant because it's not involved in the commutator. Then we have two parts. Turns out this one is just 0. Okay, so we are concerned with this part. Then we computed the commutator of this part. We put out this p. Then we get this. We write it out. We do anti-commutation relations all the way until we get this. And we do the summation over the Levi-Civita symbols, and then we obtain the contraction of indices. You have some delta, and then we get this. So what we have shown is that h with s I is in fact equals to this thing, and hence we have shown what the problem wanted us to show. Okay, so that was quite a lengthy procedure. Sorry for being boring. So this tells us that the Dirac Hamiltonian doesn't commute with the orbital angular momentum operator L, and neither does it commute with S. However, maintaining the existence of another form of angular momentum spin, such that when you add these two up, so when you add H and L plus S is equals to this guy plus this guy, and since they add up to 0, is equals to 0. So when this guy is, we call this guy J, and it's equals to angular momentum plus spin, such that the Hamiltonian commutes with J, and this is conserved. It's a conserved quantity, and yeah, it's because there's simultaneous eigenstates and stuff like that. So that means that there's another sort of quantum number in a sense, which is the total angular momentum. So as such, we have reached the end of problem 36.1. Thank you very much for listening. Sorry for the boring lecture once again, and have a nice day. Bye.